Good morning. This is your Stats Sensei, Mr. Spensei, and this is Death Packet, Unit 3B, Probability Distributions, and this is questions 91 through 100. So, for which of the following conditions is it not appropriate to assume that the sampling distribution of the sample mean is approximately normal? Okay, a random sample of 8 taken from a normally distributed population. If the population is normal, then the sample will definitely be normal. So this is good. So this is true. This is appropriate. A random sample of 50 taken from a normally distributed population. All right. So again, the population is normal, so we're good. Even if it weren't normal, because our sample size is greater than 30, we're good. A random sample of 10 distributed that is skewed to the right. Bing, bing, bing. This is bad. All right. We'd have to have a sample size of 30 or larger. A random sample of 75 taken from a distribution skewed to the left. That's okay. The distribution is normal by central limit theorem because n is greater than 30. And then a random sample of 100 taken from a population that's uniform. Although the population is uniform, but the distribution of the sample means is normal because n is greater than or equal to 30. The answer to 91 is C. Number 92. Which of the following statements is incorrect? All right, we got to be careful about the incorrect. Sample statistics are used to make inferences about population parameters. That's a true statement. All right. Statistics from small samples have more variability. Yeah, that's true. That's why we're dividing by the square root of n. As n gets bigger, we have less variability. Parameters are fixed while statistics can vary. Yes, parameters, it is what it is. The measurement of the population is the measurement of the population, but every sample can vary a little bit. So that's a true statement. As the sample size becomes larger, the sampling distribution of the skewed population becomes closer to the normal. All right. As the sample size n becomes larger, the sampling distribution of a skewed population becomes closer to a normal. Yes, as n goes up, the distribution becomes normal. So that's also true. So all of the statements are true. Number 93. At a certain high school, the distribution of backpack weight is approximately normal with a mean of 19.7 and a standard deviation of 3.1. A random sample of 5 backpacks will be selected and the weight in pounds of each pack will be reported. For samples of size 5, which of the following is the best interpretation of the probability that X is greater than 22 equals 0.05? Well, first off, they told us it was normal. All right. And so what they did was they said, okay, stat, test, Z test. And they told us our mean was 19.7. They said our standard deviation was 3.1. They said X bar was 22, our sample mean, and we had a sample size of 5. And notice they have a greater than, so I need to have a greater than, which I do. And we go, oh, that's 0.0485 is what I actually come up with. They're saying it's 5. They said it's approximately that. All right. Probability that each of the 5, no, we're not talking about each. We're talking about the average of the 5. The probability that each of the 5, nope, I hate that word each. The probability the population mean is greater than 22 pounds is approximately 0.05. No, that's not really what we're talking about. It's possible, but don't really like that. For all samples of size 5, approximately 5% of the samples will have a probability greater than 22. For all samples, yes, of size 5, approximately 5%. Yes, that sounds pretty good. Oh, 5% of the sample. That's bad. It's all right. For all samples of size 5, the probability that the sample mean, that's what we were looking at. That was the X bar. That's why I said X bar up here. So sample mean is X bar. I like this. Will be greater than 22 is approximately 0.05. All right. Make sure you read all of them because you can make an error if you're not careful. I almost did. Number 94. In a recent survey, the proportion of adults who indicated mystery as their favorite type of book was 0.325. The two simulations will be conducted for the sampling distribution of sample proportion with a true proportion of 0.325. Simulation will consist of 1,500 trials with sample size 100. We care about the sample size, not how many times you do it. Simulation B will consist of 2,000 trials with a sample size of 50. Which of the following describes the center and the variability? Well, the mean is the mean is the mean. So the centers will be roughly equal. All right? So we can ignore the ones that said otherwise. So because the mean is the mean is the mean, we can ignore the ones that say the centers will be different. They're going to be about the same. Now, the sample of size 100 will have less variability than B, than 50, the one with 50. The variabilities will be roughly equal. No, that's not true. The centers will be roughly equal and the variability of A will be greater. No, variability of B will be greater because A had 100 and B had 50. The centers will be roughly equal and the variation of simulation A will be less. Yes, it'll be less because N equals 100. All right. And the other one had 50. So this one will have less variability. A will have less variability. The answer choice is C. A new soft drink product has an average number of 77 calories per bottle. Okay, so they're telling me the mean is 77 with a standard deviation of 0.45. In a random sample of 40 bottles, okay, we have an N of 40. What's the probability that the mean number of calories is between 75 and 80? Okay, this is a bit of work. In this case, I'm going to need to find the probability of 80 and then do the probability of 75. Because what I have here is we have 77 here, and then I have 80. So that if I do, I can find this. But then if I do 75, which was on the low end, and that's right here, I need to subtract that out to find out what's left. So I'm going to do the probability of 80 and the probability of 75. So here we go. Stat, test, z-test. Mean, 77. Standard deviation, 4.5. X bar, we have 80 first. We have a sample size of 40. And notice I shaded to the left because we want the probability between that 77 is less than or equal to X is less than or equal to, less than or equal to 75. So I'm looking for that distance. So I'm going to do 80 and then I'm going to do the 75. And notice which way I have my inequalities facing. So I need it facing that way. And I end up getting a probability of about 1. So this is 0.999 for this one. 0.9999. That's the probability of that it's less than 80 minus the probability that it's less than 75. So let's find out 75. Going back, stat test, all I have to do is change the X bar to 75. And I end up with 0.8595. That's not it. That's something else. Stat test. Sorry about that. I hit enter too many times. There we go. 0.0024. So minus 0.0024. So when I take 0.999 minus the 0.024, I end up getting 0.975. Well, that's interesting. Oh, I put that number in wrong. Let me redo that. 0.9999 minus 0.0024. There it is, 99.75. All right, so our best answer choice is E. Now, you could have done this by doing a second VARS normal CDF, lower bound of 75, upper bound of 80. Mean was 77. Standard deviation, here's where we have to be careful. The standard deviation is going to be 4.5. divided by 40 raised to the half power, because it's the standard deviation of X bar equals the standard deviation of the population divided by the square root of n, which is 4.5 divided by the square root of 40. And that's what I have there. If I press enter, I get 9975. So that works as well. Answer choice E. Number 96. So, which of the following is true about the central limit theorem? All right. No matter how the population is distributed, as the sample size increases, the mean of the sample mean becomes close to the population mean. No, it's already close. The mean is the mean is the mean. The mean shouldn't change regardless of the sample. No matter how the population is distributed, as the sample size increases, the standard deviation of sample means becomes closer to the standard deviation of the population divided by the square root of the sample size. Yes, because all it's saying is, hey, the standard deviation of the sample means equals the population divided by the square root of n. That's true. I like this one. If the population is normally distributed, then as the sample size increases, the sampling distribution of sample means becomes closer to a normal. No, it's already normal, so it doesn't have to happen. All of the above, no. So our best answer choice is B. All right, number 97. In a recent survey indicated that the mean time spent on music streaming service is 210 minutes per week for the population of a certain country. A simulation was conducted to create a sampling distribution of the sample mean for a population with a mean of 210. The following histogram shows the results of the simulation. So when I look at this, it's skewed. All right. Which of the following best describes why the simulation of the sampling distribution? And remember, the sampling distribution should be normal if the population is normal or if n is greater than or equal to 30. Well, clearly, this is not normal, so the population is not normal, and my sample size must be less than 30 in this case. So, the samples were not selected at random. Well, hopefully they did a simulation, so it doesn't matter. The sample size was not sufficiently large. Looks like n is less than 30, so that's true. The sample size was, that's here. The population distribution was approximately normal. If the population was normal, then this would be normal regardless of the sample size. The samples were selected without replacement, doesn't impact. The sample means were less than the population mean, doesn't impact. All right, so our best answer choice is B. 98. A fair dice has its faces numbered 1 to 6. Let random variable f represent the number landing face up when the die is rolled. So I can get a 1, 2, 3, 4, 5, or 6. The probability distribution for the random sample variable has a mean of 3.5 and a standard deviation of 1.7078. Consider a simulation with 400 trials. I don't really care about that. To estimate the sampling distribution of the sample mean for 5 tosses. So, my sample size is 5. For each trial, the die is tossed 5 times, and the mean of the 5 values landing face up is recorded. The mean and the standard deviation of the results of the simulation should be close to which of the following. The mean is the mean is the mean, so that gets rid of this because we know it's going to be 3.5. The standard deviation, even though the sample size is small, and even though it's uniform, and I know it's uniform because the probabilities are 1/6 all the way across, but the standard deviation what were we simulating? Make sure that the probability distribution. So it should be the standard deviation of the population divided by the square root of n, which is going to be 1.7078 divided by the square root of 5. Here's what I was looking for. the sampling distribution, making sure that we're not trying to show the population. If we're trying to show the population, it should be about the population. But since it's the sampling distribution, it's the standard deviation of X bar, which is 1.7078. Divided by 5, which is raised to the half power. And I get about 0.763. So 7638, that's my best answer. And once again, it's because the standard deviation of X bar is the standard deviation divided by the square root of n. All right, moving on to number 99. The owner of a coffee shop on an amateur the owner of a coffee shop. An amateur statistician advertises that the price of coffee on any given day will be randomly picked using a normal distribution with a mean of 135 and a standard deviation of 0.1. If the customer buys a cup of coffee on 10 days, what's the probability that he will pay a total of exceeding $14? Well, that's a good question. So first off, I need to multiply this. It's really $1.35 plus $1.35 plus $1.35. So really that's 10 times $1.35 because he does it 10 days. I'm adding them up. Well, that's the same as going 10 times $1.35 because we can do that with means. We can add them directly. And we find out that that's 1350. So for the mean for the 10 days is going to be 1350. And we want the probability that it exceeds 14. So 14's here, and we have a mean of 1350, but we don't have a standard deviation. Well, the standard deviation is 10 cents plus 10 cents plus 10 cents, and you should be going, oh, you can't do that. You have to square them, then add them. Well, that means it's basically 10 of those times 0.10 squared. Then take the square root of that. So 0.1 squared times 10. Take the square root of that. And I get 0.316. And I sure hope I did this right because I'm going to feel foolish if I didn't. So 0.3162 should be my new standard deviation. So we have standard deviation equaling 0.3162 and second vars, normal, CDF, lower bound, 14, upper bound, 9 to the 99th, mean, 13.5, and standard deviation is mean of 13.5, standard deviation of 0.3162. And I come up with about 0.0569. All right, about 0.0569. Basically, we calculated a new standard deviation of 0.3162. And we did that by saying, hey, squared plus squared plus squared 10 times, or 10 times that, but make sure you take the square root of it. All right, so I'm going to go through that real quickly again. So second vars, norm CDF, lower bound 14, upper bound, it goes to infinity. All right, the mean was 13.5, and we did that by 135 plus the 135 plus 135. And then we had to take our standard deviation, 10 times 0.1 squared. All right, so that gives us that. So a 100, the time required for the first stage of an assembly line is normally distributed with a mean of 28. And a variance of 5. So the standard deviation equals the variance is 5. So the standard deviation of that, I just need to come back and take the square root of that. So the standard deviation equals the square root of 5. I mean, standard deviation equals the square root of 5. While the time regarding for an independent second stage is normally distributed with a mean of 17 and a variance of 4. What is the probability these two stages will take more than 50 minutes? Okay, it's not what I thought we were doing. So I should have read the whole problem first. So I have a mean of 28 and a mean of 17. Well, I can add means together. And so this ends up being 28 plus 17 should be 45. The two stages together is 45. So the mean is 45. And then we have a variance of 5, and we also have a variance of 4. We can add variances directly. So in this case, we can add variances directly. So 5 plus 4 equals 9. So the variance is 9, but I need to turn that into a standard deviation. So I'll take the square root of that. So my standard deviation is 3. The square root of 9 is 3. So what's the probability that two stages take more than 50 minutes? Well, we know that our new mean, our combined mean is 45. And we know that we want to know what's the probability that's 50 or more. And we know our standard deviation is 3. So we want the probability that Z is greater than 50 minus 45 over 3. So we're going to do a norm CDF, second vars, norm CDF, lower bound 50, upper bound 9 raised to the 99th, mean of 45, standard deviation of 3, and we end up getting 0.0478. That's one way to do it. The other way to do it is go stat test, Z test, mean 45, standard deviation of 3, X bar of 50, sample size 1, sample size 1, and we need to make sure that we're shading up, and we still get to 0.04779, which is the same thing. All right, thanks for watching. I hope that helped. I know I was a little bit fast on some of these, and look forward to seeing you on the next one. Bye.